Hi, my name is Tom Heffel, and this channel is to help students learn chemistry. In this video, we're going to be talking about outliers of things that typically happen on the periodic table. Okay, and more specifically, we're going to talk about what type of trend exists between cations and anions versus their parent atom. We're going to talk about transition metal ions, specifically their electron configuration, as well as the electron configuration of chromium and copper. And then we're going to talk about the ionization energy of the elements that are listed here: boron versus beryllium and nitrogen versus oxygen. So let's get started with talking about cation size versus its parent atom. So what I'm going to do is I'm going to briefly put up a Bohr model of calcium. And calcium has 20 protons and 20 neutrons, and its rings are 2, 8, 8, and 2. And if you forget how to do this, I do have a video on creating Bohr models, and we use Bohr models to learn a lot of different things in chemistry. So this is a neutral calcium. Okay. Now, when calcium becomes an ion, it's going to make a calcium positive 2 ion. And our job is to figure out which of these two is bigger. Is the calcium atom bigger, or is the calcium ion bigger? Okay, so right here is the neutral calcium. And if this was to become a calcium ion, it would lose 2 electrons, which means a whole ring would be eliminated. Okay, so obviously the calcium ion, with the removal of the ring because it lost 2 electrons to become a positive 2, is much smaller, and therefore the calcium atom, okay, is actually bigger than the calcium ion. So whenever you create positive ions, they become smaller than their parent atom. So a lot of times we call this neutral element the parent atom. And then if they lose or gain electrons, they create cations or anions. In this case, it's a cation because it's a positive ion because it lost 2 electrons. Okay, so the parent atom is going to be larger than the cation, or the cation is going to be smaller than its parent atom. Either one of those statements is true. Now, if we do the same thing for sulfur, if I do sulfur, sulfur has 16 protons and 16 neutrons, and its Bohr model is going to be 2, 8, and then 6. Okay, so 2, 8, and 6 for a total of 16 electrons. This is the neutral sulfur atom. Okay, and we're going to compare the sulfur atom to its ion. Now, sulfur having 6 valence electrons, it's not going to lose that ring of 6, okay, and become a positive 6 ion. Instead, we're going to add 2 electrons, and when you add those 2 electrons, the sulfur becomes negative 2. Okay, and that's the application of the octet rule. Okay, so calcium loses 2 electrons to form the cation. Sulfur is going to gain 2 electrons, and we're going to call that an anion. Okay, so what one is bigger, the parent atom or the negative ion that we call a cation? Well, when we add these 2 electrons in there, we're going to get this electron repulsion, and actually the atom is going to get bigger, okay? Or I should say the ion is going to get bigger than its parent atom. So in this case, the anion is larger than the parent atom because we're gaining electrons, and we get this electron repulsion. So when you add electrons, the thing gets bigger, and hopefully you understand here, when you remove the electrons, it gets smaller, and significantly because we're losing an entire orbit of the calcium atom. Okay, so in a nutshell, cations are smaller than their parent atom because they lose electrons. Anions are larger than their parent atom because they're gaining electrons. Okay, so not so bad with that piece right there. The next thing that we're going to talk about is going to be transition metal ions, okay? And specifically their electron configuration. So I'm going to do the electron configuration for iron. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and it goes all the way to 3d6, okay? And if you don't know how to do electron configuration, I have a previous video on electron configuration as well, okay? Now what we want to do is I want to do the electron configuration for an iron that's a positive 2, because this outlier is not just going to be what's the electron configuration for a transition metal, it's going to be what's the electron configuration for a transition metal ion. Now, if we're making a positive 2 ion, that means 2 electrons have been removed, okay? And what most students want to do is they want to come in here and they want to remove these last 2 electrons that was put in, and that's wrong, okay? And that's why I'm doing this video, okay? So the thing that you want to write down in your notes, okay, is when we remove electrons, it is not the reverse order of the way the electrons came in, okay? Now, the way the electrons come in is just going to be according to our periodic table. You just keep going across and you figure everything out. Like I said, I have a video on that. But when you take them off, it's not going to be in the reverse order, okay? The rule is that they're going to be eliminated from the electron configuration that has the largest principal quantum number, which means they're going to be removed from the valence shell first. So if I'm going to remove 2 electrons, the 2 electrons that I'm going to remove are going to be these electrons from the 4th energy level, okay, which is on the 4th ring, okay? I am not going to remove them from core electrons, which are on the 3rd ring, okay? So once again, when you take electrons off, you do not remove them in reverse order in which you put them on. You're going to take them off of the one that has the highest principal quantum number. And the principal quantum number is these big numbers in front. Since this has a 4, that's where I'm taking it off because it's on the outside. So the electron configuration for iron that's a positive 2 is going to be pretty much identical to what we have before. But we're going to remove these 2 electrons from the 4s2. And we get this electron configuration. If this was an iron that's a positive 3, we'd remove these 2 electrons first. Then we would start on the 3rd, starting with the 3d, then the 3p, then the 3s as you take electrons off. Okay, so I just wanted to cover transition metal ions electron configuration. The next one I want to talk about is chromium's electron configuration. So if we're doing electron configuration, we might put this down, okay, as an answer for chromium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. We might be tempted to write this down, okay? And I'm going to do an energy, electron energy diagram for this because it will show you kind of like a little bit more descriptively of what I'm trying to get across. Okay, so we're doing an energy diagram where energy increases on the y-axis. The 1s has 2 electrons. The 2s has 2 electrons. The 2p6 has 6 electrons. They're going to go in kind of in this fashion. And I do have a video on energy, electron energy diagrams as well if you don't know how to do this. Just give me 1 second. And then we have the 4s. And remember, the 3d is going to have 5 orbitals since it's in the d block. Okay? And I stopped right here, okay, because it's this last portion that's incorrect. Okay? Like I said, we might be tempted to do 4s2 and then 3d4 as an answer. But what you end up finding out is that the 4s and the 3d are practically the same energy at this level. Remember, as you go out further out, these orbitals get closer and closer in energy. Okay? And what the scientists have discovered is that this is not the ground state. This is not the lowest energy possible. Okay? In fact, what we're going to do is we're going to take an electron off of the 4s and we're going to make this half filled. Remember, electrons that spin in the same direction in degenerate orbitals has a way of lowering our energy, and that's according to Hund's rule. So what the scientists have figured out is that having the 4s and the 3d be half filled is actually lower energy than the 4s being completely filled, and then the 3d just kind of 4/5 of the orbitals spinning, having electrons spin in the same direction. So this is actually an excited state, okay? And the ground state is going to be when both these orbitals are half filled. So the correct electron configuration for chromium is 4s1 and 3d5. And this is an anomaly. This is an outlier of what normally happens, okay, when we do electron configuration. The normal way of doing electron configuration would have been 4s2, 3d4, but your book points out one of the exceptions. So don't make everything an exception, just chromium, and the other one is going to be copper. So let's go ahead and change this chromium to copper. Now, normally, you would do 4s2, and the way copper would end would be with 3d9. So if we were doing this normally, it would look something like this. But the scientists have discovered that this is an excited state. There's actually a ground state that's actually more stable or lower in energy. And that is, instead of having this completely filled and this nothing, they said, how about this being half filled and this being completely filled? And they've discovered that this is actually lower in energy. So the correct answer is going to be 4s1 and 3d10, okay, which is the ground state for copper. Okay, so there's something special about having these energy orbitals, okay, being half filled or completely filled. In this case, a half filled, completely filled is lower in energy than if the 4s was completely filled and then this being nothing, okay? So half filled, completely filled is better, okay? A lower in energy. All right, so that brings us up to ionization energy. Now we know the trend for ionization energy is up and to the right on the periodic table due to a lack of shielding going up and due to a higher effective nuclear charge going to the right on the periodic table. Okay. However, in a given period, there could be some exceptions. And the first exception we're going to look at is boron versus beryllium. Okay. So boron's electron configuration and energy diagram looks like this. So this is boron, and right next to it we'll put beryllium. I'm sorry, this is beryllium. And right next to it we'll put boron, which is 1s2, 2s2, 2p1. Okay? So according to the normal trend, we would say that boron would have a higher ionization energy because it has a higher effective nuclear charge. But when we investigate their electrons a little bit more, we got completely filled, completely filled. That seems pretty stable. It means it's probably holding on to its electrons pretty well, where it might require more energy to kind of remove that electron versus the boron that has completely filled, and then maybe an electron that's kind of like dangling out there a little bit more than the beryllium, okay? And when we look at ionization energies for boron versus beryllium, boron has an ionization energy of 801 kilojoules per mole, where beryllium is 899. Okay, so it's once again about having these completely filled orbitals versus completely filled, kind of like one dangling out there. Okay, so even though that boron has a higher effective nuclear charge, got that electron that's kind of like dangling out there, a little bit easier to take than the beryllium. Okay, and then this repeats itself. This concept repeats itself again between nitrogen and oxygen. So let's take a look at nitrogen and oxygen. We got to look at nitrogen first and then oxygen. So nitrogen is going to be 1s2, 2s2, 2p3, half filled, okay? Versus the oxygen, that's going to be 1s2, 2s2, 2p4, okay? So Which one do you think can hold on to its electron a little bit better than the other one? Okay, the nitrogen is going to be able to hold on to its electron a little bit better. Completely filled, half filled. If you take an electron off, you're disrupting that half-filledness of the 2p orbitals, okay? And therefore, the ionization here is going to be just a little bit higher than the oxygen that has completely filled. Well, nothing. In fact, if I remove one, then I get half-filled. So maybe it's a little bit easier to remove an electron from oxygen, 1,314 kilojoules, versus the nitrogen, which is 1,402 kilojoules per mole, okay, to remove those electrons, okay? So these are just some outliers of things that we normally see. Normally, ionization energy increases up and to the right, okay? And obviously that's not the case because as we move to the right, we're not increasing. And a lot of it has to do with these half-filled or completely filled energy orbitals, okay? As you move to the right, you'd expect to have a higher ionization energy. Not always the truth, okay? Once again, an investigation on the electrons in each of these atoms. So in general, ionization energy goes up and to the right, and we got a couple of these irregularities that are worth talking about because the author in your textbook was talking about. And I wanted to point those out because sometimes when you read, you don't pick up everything, and I just want to take a few moments to talk about some of those things that your author has already pointed out. So if you found any of this informative or helpful, please like and subscribe. It does help the YouTube algorithm because my only goal is to help students learn chemistry a little bit more easily. And if this helps, please share it with other chemistry students.